Please identify yourself.
Who am I?
Please articulate your password.
Let me in.
You seem to be Peter Y.
This is an interface where man meets machine. Hands, eyes, vocal cords, menus, commands, graphics. These are the elements, and the goal? To communicate easily with a computer. Welcome to TRW's Man-Machine Interface Laboratory. I'm David Krebs. We're going to demonstrate some things here, research into an aspect of system design, the link between operators and the computational tools critical to solving today's complex military problems. Peter Wong of our Software and Information Systems Division heads up our lab. Peter, can you tell us what you mean by the Man-Machine Interface, or MMI?
Well, the concept is pretty simple. The trigger for your electric drill, for example, or your steering wheel in your car is an example of a man-machine interface. It just means how a human interaction gets translated into signals so a machine can understand. Now, electric drill is pretty simple, of course. In our facility, we are using machine to do information processing. And when our product is information, man-machine interface is a two-way street. As we think of it here, MMI is concerned with how information is exchanged between a human and a computer. Computer.
Ready.
What type?
Electrical subsystem ready.
Computer.
Ready.
Show fault. In its simplest context, it's eyes looking at the video screen or fingers typing on a keyboard. Computer.
Ready.
Show problem. But that's only the tip of the iceberg. We want to utilize all of man's faculty, his hearing, his voice, even his vision, to track and point objects on the screen. Computer.
Ready.
More details. All may have a place in interaction between the operator and his system. Part of the problem, of course, is to translate the human signal so that a computer can understand it, and vice versa.
Right out. Ready.
But that's only a fraction of what's MMI's function. Getting the computer to do what you want at the right time. Making the interface easy to understand and readily usable. Computer.
Ready.
Show redundancy. Designing a resilient interface, one that can survive and work with the user, and most importantly, deliver useful and understandable results. Those are the challenges of MMI research.
Thanks, Peter. Typically, a project uses the lab to help configure hardware and display data. MMI is important, perhaps critical to the success of large computer-based systems. The problem? It's subjective. One user may have one idea of what makes a good interface, and another might want to see something very different. The proper interface depends on the skills of the individual. We must match those to the complexities of the computer. An experienced user will want an interface quite different from that desired by a less sophisticated user. Our test bed here consists of two aspects. Each workstation combines state-of-the-art hardware with a dialogue design language called FLAIR. The language is a computer-aided design tool for simulating man-machine interfaces. At the workstation, FLAIR interconnects the various types of equipment. The user picks and chooses, searching for the precise pieces to fit his particular puzzle. FLAIR integrates these devices so their value can be proven easily. FLAIR always delivers the proper protocols, whether commands are received from a trackball or a light pen. Users can experiment with various devices and change from one to another in moments. In the laboratory, we can control the environment, the lighting, arrangement of input-output devices. We can even simulate background noise. Each workstation has two display screens plus a conventional alphanumeric terminal. The 25-inch high-resolution color display has 1,024 lines of definition, 2 to 3 times better than the standard television monitor. The alphanumeric terminal, a 15-inch CRT, displays text, while the 19-inch monochrome monitor presents secondary material which is not color dependent. FLAIR is a very friendly graphic system. With it, TRW interfaces are brought about by building interactive dialogues. It's called a show-by-example menu system. The user graphically shows the computer how interactions are to proceed and data displayed. Why bother with all this? Early simulations are necessary because MMI needs to be dealt with before hardware choices or software architectures become inflexible. TRW's testbed, wherein MMI concepts in general are tested and program-specific interfaces simulated, is an attempt to deal with this problem. In the past, these issues have been worked late in the software development process, too late. Potential users deserve the opportunity to react early to proposed interfaces. How much information should be shown? How much detail? How should it be organized? Screen resolution, character sizes, graphics, timing, even costs and software maintenance questions impact these decisions or are impacted by them. As scenarios, simulated slices of a system's interface, take shape, the user constructs displays frame by frame. Each one contains descriptions of the graphics and related possible interactions. These interactions are tied to control structures which in turn command FLAIR to execute other functions or displays. By dynamically interacting with the scenario, the user is able to determine its usefulness and do so before the system becomes operational. FLAIR operates as a UIMS, a User Interface Management System. It manages and controls the interface, translating user instructions to signals the computer can understand and vice versa. But the man-machine interface, no matter how well simulated, is hard to validate until it is integrated with its application programs. These are the real working programs of the system, the large number crunchers which deliver product data to the MMI for display. If application programs exist, these too can be linked via FLAIR to the displays. FLAIR, the UIMS, takes the products of the application software and delivers a standard set of protocols to the appropriate display. By managing the interface between the user and the display and the application software in the display, FLAIR allows for rapid simulation of the MMI and very flexible alteration of it. As more and more application software becomes available, it too can be tied in through FLAIR to the simulated interfaces, replacing piece by piece the simulated data presented there. The whole process is very flexible, the result of the way FLAIR itself is structured. The user commands are controlled via a set of state tables. Each command has a state table in which a sequence of subroutines called microprimitives are called upon to perform the computer's reactions. Microprimitives are the building blocks, the most basic actions: circle drawing, scenario control, colors. Microprimitives in nearly unlimited combination create the display. The result? Flexibility. The state tables can be changed, the sequence of microprimitives, or the microprimitives themselves. FLAIR is the glue that holds it all together. As a user interface management system, FLAIR manages the interactions between users, the interface, the hardware, and the portions of the application software already in existence. In fact, FLAIR is so helpful in designing user interfaces that a version of it is being designed for possible incorporation in delivered systems. Then, the UIMS might become an integral part of a system, maintaining the MMI and ensuring FLAIR's inherent flexibility throughout the life of the system. Under the auspices of the MMI Lab, TRW has assembled a tool with which system users can direct system designers in the creation of an appropriate and useful interface. It's just one way we're working to solve the problems of today, and it's happening at TRW. Increasingly, graphical input and output techniques are being combined in order to construct powerful, interactive user interfaces. In the program being demonstrated, the operator is using a number of techniques in order to design a flowchart. The example shows how both hands and various devices can be combined to make use of the operator's full operating potential. Such interfaces are hard to construct, however. In this tape, we will demonstrate two tools developed at the University of Toronto in order to facilitate this task. The first is a runtime support package that handles user interaction. It is a table-driven package that handles all input, event detection, screen updates, and procedure invocation. Even on its own, such a package has several benefits. It frees applications programmers from low-level detail. It facilitates software maintenance by enforcing a common programming methodology for user interfaces. And finally, it facilitates portability of application software, since all interaction is via a standard software package. This next example is a simple chemistry simulation on titration. Adding acid brings a solution to equivalence. Acid is added by pushing the tablet selection button while pointing at the burette. Equivalence is indicated by a color change in the beaker and a sound effect. Let's reconstruct this simple program as a means of illustrating our second main tool, Menulay. Menulay is a program for interactively designing the user interface for menu-driven software. It is a preprocessor whose output is automatically translated into high-level source code. Menulay generated itself, so all interactions used in working through our example are available candidates for our titration experiment. Our first step is to draw the objects which are to appear in the display. Here, a simple sketch editor is being used to draw the burette. Our next step is to design the layout for our display. First, we select and position the graphical elements to be employed. We use our hand-drawn objects, all of which are immediately available through the picture library at the bottom of the screen. We then add the necessary text by positioning the tracking symbol and typing on the keyboard. We then assign colors to the objects. Since we're using a monochrome terminal, colors appear as words. They will, however, be properly displayed when shown on the final device. Next, we will specify the semantics of the experiment. We do this by typing the names of the procedures to be associated with each active object. The procedures must be pre- or post-defined by the applications programmer, or defined on the spot within Menulay. Nearing the end, we will now do the final scaling and positioning of objects. Note that in positioning objects, we can make use of a grid for increased accuracy. Having finished our specification, we now save our work. We are ready to invoke the process that will translate our specification into C code, compile the result, and link it with our runtime support package. In doing so, all options are selectable by the menu. We now exit Menulay and are ready to run our simulation.
The new generation of powerful personal workstations has much to offer to builders of user interfaces. Machines like the Xerox 1100 series, the Symbolics 3600, or the one shown here, a PERC Systems PERC, have the potential to provide highly cooperative and supportive user interfaces for applications that run on them. The integral high-resolution bitmap screens of these machines can be divided into multiple independent windows and can display icons and other graphical objects in addition to text. A mouse or other pointing device allows various kinds of graphical interaction, including menu selection and identification of system objects by pointing. And the considerable computational power of these machines can support spelling correction, integral help systems, and other cycle-intensive, user-friendly features. In practice, however, interfaces on these machines often fail to live up to this potential. Glass teletype style interaction is still all too common and is a poor use of the available interface resources, even if it is conducted through multiple independent windows. A major reason for unsuitable interfaces on these machines is the complexity involved in developing appropriate ones. It is simply too costly in terms of time and effort for an applications programmer to develop a powerful graphical interface for each and every application program he builds. Typically, the effort involved in building and refining such an interface for a simple application will be considerably greater than the effort of constructing the service part of the application. The Cousin Interface project addresses this problem by allowing application builders to define interfaces through a specialized language embodying very high-level interface abstractions. A short textual description in this interface definition language can be interpreted by the Cousin Interface system to provide a sophisticated graphical interface like the one shown here for the print application. Cousin's interface abstractions are based on a form metaphor of communication between application and user. A Cousin interface is a form whose fields correspond to the various pieces of information that the user and application need to exchange. Many of the fields in this form correspond to parameters to the print application, such as the name of the file to print, the number of copies, etc. Other fields correspond to commands the user can give to the application. Here, just the command to produce hard copy on the printer and the command to produce a formatted file ready for printing. The remaining two fields in this form are scroll TypeScript windows for non-graphical feedback to the user from Cousin and from the application. In a minute, we'll look at how a user can interact with such a form to control the application to which it provides an interface. And we'll see some of the kinds of user-friendliness with which Cousin supports such interaction. But first, let's take a broader look at the structure of the Cousin interface system. As shown here, Cousin sits between the application and the user, controlling communication between them according to the specification in the application's declarative form-based interface definition. The application is thus completely decoupled from the numerous details of communication with the user. It sees its interface solely in terms of a collection of value-containing fields which it can access or set, and which Cousin can guarantee to contain correct values. All details of how values get into those fields, how the user knows what values to insert, how user errors are reported and corrected, how online help is given. All these details can be left to Cousin. This represents a tremendous savings in implementation effort to the application builder. There are also two major advantages to this arrangement from the user's point of view. First, instead of a glass teletype, the user gets a sophisticated graphical interface, complete with menus, error correction, integral online help, and other user-friendly features. Secondly, all interfaces that use Cousin follow the same general plan and have the same interaction details. To close, let's review the main features of Cousin. Cousin provides user-friendly graphical interfaces for a wide variety of application systems in an application-independent manner. These interfaces are defined in a declarative language using high-level abstractions based on a form metaphor of communication between application and user. The amount of effort required to construct one of these interface definitions is quite small. In particular, it's very much less than would be required to hand-build a graphical interface of equivalent sophistication to the one Cousin provides. Moreover, the Cousin interfaces are consistent over all applications in terms of both the low-level details of interaction and the high level of user-friendly services provided. Cousin was developed in the Computer Science Department of Carnegie Mellon University under ARPA funding. The implementation shown here runs in the context of the SPICE Scientific Integrated Personal Computing Environment, also developed at CMU.
SiGGRAPH, the Interactive Graphics Engineering Resource, is an integrated collection of software utilities designed to implement computer-aided design and manufacturing applications. Currently in pre-production development by Boeing Computer Services Company, it is anticipated that SiGGRAPH will host the next generation of CAD/CAM applications at Boeing. SiGGRAPH has been implemented on the IBM 5080 graphics system, a high-performance 3D graphics workstation featuring a high-resolution color raster display and a variety of peripheral input devices. These include an alphanumeric keyboard, a lighted program function keyboard, dials, and tablet with function key locator. The 5080's high-speed graphics processor provides 2- and 3-dimensional view transformation and clipping and other graphics functions. An attached IBM 4341 computer performs most of the utility and applications processing. The SiGGRAPH software includes utilities to support graphics, user interface, geometry, and database. The graphics and user interface utilities integrate SiGGRAPH applications at the front end by providing the user with a consistent system interface. The geometry and database utilities integrate SiGGRAPH applications at the back end by providing a uniform data representation. The prototype SiGGRAPH application is the geometry layout application seen in this film. A general-purpose facility for 3D geometric design, it provides an effective demonstration of the use of various SiGGRAPH utilities. The most visible components of SiGGRAPH and the key to the enhanced user productivity promised by the system are the User Interface Manager and Graphics Display Facility. The use of these tools provides SiGGRAPH applications with powerful capabilities in a standardized interaction framework. The display screen is organized in a standard layout. Most of the screen is used for graphics display, with areas near the bottom used to display messages, menus, prompts, and inputs. The user presses the appropriate key on the program function keyboard to select a group of related functions for display in the menu area on the screen. Here, the user selects the lines functions. One of these functions is selected by default as the current function and is displayed in green in the menu area. Here the default is line between 2 points. Other available functions appear in light blue. The user may accept the default as the current function or select another function. Here the user selects line parallel to axis. When another function is selected, it becomes the new current function and future default. A sequence of prompt messages appears in the dialog area immediately below the function menu. These instruct the user to supply the input parameters required by the current function. Here, the user is prompted to specify the parallel axis, relative position, length, and base point for the line to be constructed. An arrow identifies the current step in the interaction, leading the user through the sequence step by step. Here, the user specifies the y-axis and y-positive position by choosing from a list of options, specifies a length of 2 by typing on the keyboard, and identifies a base point by selecting the entity on the screen. When all the necessary inputs have been provided, the function is performed and the results displayed. Defaults are provided for most inputs, and if the user chooses to accept a default, he simply specifies a subsequent input with the appropriate device action. Here, the user accepts the axis and position defaults by entering a new length. When defaults are overridden, the user-supplied inputs become the defaults for successive invocations of the function. So, to create another line using the same axis, position, and length, the user simply selects a new base point. Thus, explicit user actions are required only to override the defaults or to supply inputs which have no defaults. This technique reduces considerably the amount of explicit user interaction required for repetitive functions. The use of sequenced, prompted inputs combined with implicit acceptance of adaptive defaults provides a unified interface acceptable for use by both novice and expert users. In addition to a standardized command interface, SiGGRAPH provides standard viewing functions for visualization of defined geometry. Multiple views provide the user with simultaneous displays of the geometry from several viewpoints. View manipulations, including translation, rotation, and scaling, may be performed interactively using the dials to control the view or statically by explicit key-in of rotation angles, translation vectors, and scale factors. Shaded rendering of surfaces using a variety of illumination and reflectance models provides an effective means of visualizing complex shapes. All viewing functions are transparent to the application and may be invoked independently by the user. A typical session illustrates the effectiveness of the SiGGRAPH graphics interface tools. The user begins by creating the defining points for the construction by typing in coordinate values. Using these points, he creates the curves which will be used to generate the surfaces. The periphery of the base is constructed with connected arcs and lines, which are duplicated to create both upper and lower edges. These become visible in a rotated view. Circles and a fillet between two lines are constructed to define the cylindrical post. Surfaces are created by ruling between the edge curves and revolving the fillet curve about the post's axis. Since the part is symmetric, only the left half has been constructed directly. Now the half part is duplicated to complete the part definition. The fully surfaced part model is then verified by displaying a shaded rendering. This sample part, a 747 stud-light trough support, consists of an elongated flat base with rounded ends supporting two cylindrical posts. The highly visible graphics and user interface utilities allow SiGGRAPH applications to share a common user environment for maximized user productivity. Behind the screen, less visible but equally important utilities support geometry and database management, providing applications with a common data environment for maximized application flexibility. Together, the SiGGRAPH utilities constitute a powerful tool for the implementation of integrated CAD/CAM applications.
My name is Henry Lieberman at the Atari Cambridge Research Center, and I'd like to tell you about a program that I've been working on called Tinker. Tinker is an interactive programming environment for Lisp that allows you to write programs from examples by presenting an example to the computer, working out the steps of the procedure on the example, and generalizing a program. The example that I'd like to show you is from the domain of video games. We'll use Tinker to develop a program for Atari's first popular video game, Pong. And we will write the program for the Pong game by demonstrating to Tinker various situations that can occur during the game, showing Tinker how to handle these situations, and showing Tinker how to distinguish between the various types of situations that might occur. First, here's an advanced look at the Pong game we're trying to produce. The rest of the tape will show how we can put this program together using Tinker. We'll be both writing the code for the game and testing out the game from the game player's point of view at the same time. Now we'll define a bounce ball function that takes the x and y coordinate of the ball and the y coordinates of the paddles. Since the ball starts out in the center of the screen, there's no collision with anything else. So we get a function bounce ball, which just returns the symbol no collision. Using the mouse, we'll move the ball so it collides with one of the walls and show Tinker what to do in this case. It's a new example for the bounce ball function, and we'll tell it to bounce off the bottom wall, which is represented by a normal vector of 180 degrees, perpendicular to the wall in the direction of the bounce. In this case, what we want the ball to do is reflect its heading off the wall. Now Tinker asks us, what's the difference between the case where there is a collision with the wall and the first case where there's no collision? And the predicate we give Tinker to distinguish between these two cases takes the y coordinate of the ball and sees whether it's close enough to the bottom of the board. This results in a new bounce ball procedure that says if the ball is close enough to the bottom of the board, then bounce it off the bottom wall. Otherwise, there's no collision. We showed you how to check for collisions against the top and bottom walls and the left and right paddles. We now have a sub-game of Pong that just consists of moving the ball around and checking for collisions. So I'm going to run just that part of it. So we're going to be in a loop that bounces the ball, that runs the bounce ball function, and then tells the ball to move forward. Well, so far everything looks great. So now we set up the situation where the ball is against the wall but didn't hit the paddles. In this case, we want one of the players to score. So we tell the scoreboard to increment the score of the player who won that particular point. The score used to be Henry 0, Greg 0. Now it's Henry 1, Greg 0. To begin the next round of the game, we move the ball back to the center of the screen. And just for fun, let's change the heading of the ball to be a random number so that the ball goes flying off in some random direction every time a point is scored. And we can see the heading of the ball change. Now what Tinker wants to know is what's the difference between the case where it hits the right paddle and the case where it hits the right wall without hitting the paddle. So we tell it to check to see if the distance between the paddle and the ball is less than the size of the ball. And now here's the finished Pong game in action. Up, Henry returned the ball. Greg hit it too. Henry got it just in the nick of time. So did Greg. So far both of the players are pretty good at this point. I guess I really should have had it beep when it scored a point. And there's a little bug. We didn't didn't check for the case that the ball might bounce back and forth forever without hitting any of the paddles. We could put in a check for that particular case by using this as another example and going through the new example procedure.
Severo Ornstein. I'm a computer scientist, but I'm also an amateur musician, and my father is a composer. For years, I've watched him struggle with the problems of writing music down on paper. And I've known for many years that we could use computers to help, but until recently, we haven't had powerful enough machines. Over the last year, a student from MIT, John Maxwell, and I have been working on this problem, and we've produced the system which we're now about to show you. In order to make it quicker to put music in, we hooked a synthesizer up to the computer so that we can play the music directly into the machine. We also have to be able to enter music by hand, but that's slower, just like writing on paper. The sound that the synthesizer makes is not the most wonderful, and we've not focused on the issues of performance at all. We only use the sound as a means of proofreading to check the scores that we create. The emphasis is entirely on the scores. Now John will demonstrate the system for you.
Mockingbird runs on a special high-speed computer called the Dorado. This is Dorado's terminal, and this is the keyboard through which we communicate with the Dorado. This is a special pointing device called a mouse. Notice that as I move the mouse around, the cursor moves around on the screen. We've also attached a synthesizer, which Severo mentioned, through which Mockingbird can both record and play. Let's look at the piece of music currently on the screen. This is the piece of music that we played for you earlier, Bach's Little Fugue in G minor. What you see on the screen is not the entire piece, and we can bring up more of it by scrolling up. This is the second page, and the third page. We can continue rapidly scrolling through the piece like this. There's another way we can obtain a view of the entire piece, and that's to jump to an overview. In this overview, we have a rough sketch of the piece, which is composed only of the beams and the stems. The composer can find his way around in this in two manners. One is by looking for the beams and stems in a rough pattern that he's recognized before, or by playing from a particular section, which I shall do. I'm listening for a long trill that I know is in here somewhere. When I find it, I can jump back to the main score at that point. There it is. And there's the long trill I was talking about. It's a half note tied to a whole note, tied to another half note. Let me play that for you. When I'm through with this piece, I can name it and store it. Later on, if I want to look at it again, I can call it back by name. Let's see how one might record music from the synthesizer. To do that, we first select an area that we'd like to record into and hit record. Severo. This is a time plot of the music that Severo just played on the synthesizer. We'd like to convert it into score. The first thing we have to do is make sure that all the notes are properly lined. If we look at this note right here, we can see that it's slightly off. Now I could pick it up and manually move it over to where it should be, but I'd rather have the computer make its best guess about where it thinks it should be. The way I do that is I select the entire score and issue the command. And the computer brings everything together within a certain tolerance. The next thing I have to do is beat in some measures to give the computer reference points on the score. The way I do that is to play back and beat in measures. Ask the computer to put the measure lines right up in front of the notes that they think it's in front of and check to make sure they're all right. I see that one of the measures here got slightly misplaced, and so I'm going to move it over. Now I'd also like to insert a measure at the beginning of the piece. The way I do that is I pick up a measure line from this menu. The way I pick up any object from the menu is by sliding the cursor over like this until the cursor's icon correctly matches the object that I want, and then release the menu like this. I can then insert the object that I want. That's the only measure I want to insert, so let me get rid of the icon. Now I'd like to insert a time signature and a key signature. To insert a time signature, I point to an area and tell it I'd like it to be in 3/4 time. See the time signature there. To indicate a key, I select the entire piece and tell it this in the key of G. Notice that the appropriate accidentals have appeared over to the left and that all the F sharps have disappeared from the score. Let's put the note values in for this first measure. What should the note value be for this first note that I've just selected by turning gray? You might suspect that it should be an 8th note because it's approximately an 8th note's distance from here to this note. But this note is not the next note in this note's voice. The next note in this note's voice is way over here, and the value for this note should be a dotted half, like that. We can continue with the melodic line up here. This should be an 8th note, this should be an 8th note, that should be a quarter. These all should be 16th, and all should be beamed. If I want, I can move this beam up like that and tilt it. These notes should all be quarters and recorded. Now should be on the second staff, place them down. Same with these. These are on the second staff, but they're 8ths instead of quarters. I think I'll move this beam down like that.
In approaching a system, the composer has 3 fundamental tasks to perform. The 3 tasks are composing the score material. The second task involves designing the palette of timbres, or the instruments that the composer will use in the score. And the third task is the performance of the material that's been composed. The performance program that we have is called Conduct. It derives its name because it allows you to conduct or perform scores that have been pre-composed using the techniques we've already seen. It's an important program because it demonstrates one key thing: the concept of downward compatibility in computer graphics rather than upward compatibility. Here we're using a straight ASCII alphanumeric display, but it's coupled with a tablet in such a way that we can make use of several concepts which we've already seen with the sophisticated graphics terminal. I'll demonstrate this. The display has a moving cursor which tracks the position of the cursor on the tablet. So bottom left-hand corner, bottom left-hand corner. Now, the information which is displayed on the terminal is in essence the operating console of the instrument. There are a series of 8 scores whose information is set out in rows, and for each row I have a number of parameters which I can affect in real time. Let's take score 1 and go to the particular control called on-off. By pointing at the on-off switch and depressing the cursor button number 1, I can hear the score. The score plays once and then switches off. By moving to the next column for that score, I'll turn the cycle mode on, which will result in the score repeating once it's begun. We can now look at the other parameters. For example, working right to left, we have the parameter called richness. This is the richness of the spectrum. If I point to that parameter, I can type a value, let's say the value 20, and the spectrum of the sound will be adjusted to be increasingly rich. Rather than typing, however, I have other techniques which I can use to change the value. One of the key ones is the technique of dragging. In essence, every number on the display is a graphic potentiometer exactly of the same type as the graphic potentiometer seen in previous programs. That is, I point to the value, depress the Z button, and I can pull the value down. As you can hear it get clearer, or I can push it up. Functionally, we have a graphic potentiometer, although the output graphics are different, or they adapt to the fact I only have an alphanumeric display. The study we're about to show you is simple enough to make things clearly understandable, and yet has sufficient complexities to bring many interesting features of selection positioning tasks to the fore. The case study involves selecting from among one of 3 geometric figures, a square, a circle, and a triangle, and positioning them in this 2-dimensional workspace. We'll look at several different techniques for doing the selection and positioning, and we'll discuss the properties of each as we go along. In doing so, we will constrain ourselves to using the graphics display, the typewriter type terminal, and the graphics tablet. The first technique which we're going to use is called dragging, and what we will do is simply move the pointing device over top of the item which we wish to select, depress the yellow button on the cursor, and drag the shape to the desired location. When it's in the desired location, we release our finger and the shape is anchored. I'll repeat that with a circle. I'll go to the circle, select it, hold the button down, drag it across, release it, and it is anchored. Using this technique, we can select several items and lay out complex patterns. One important point about the technique as seen thus far is that there's a tight coupling between the gesture which selects the item, that is the pushing the button down, and the anchoring of the item, that is on the release. The point is that the down and up motion are tightly coupled, and therefore the 2 steps of the operation, selection and positioning, are bound together in a single gesture, much in a way analogous to a compound word. One of the problems with this technique, however, is the necessity to go back to the menu every time we want to select an item. For example, if we want to have the same item several times on this display, the hand motion is rather wasteful. We can, in fact, make a different version of this technique which exploits the redundancy of several types of usages. In this case, we can point to the triangle, drag it across, anchor it as before, but we still have a triangle on our cursor. So every place I depress the button, I will get a triangle. In essence, going across to the menu is like dipping your brush in a painter's palette, and now I've got the color or the shape on my brush. I can dab over top of the locations that I want that color, or in this case that shape, to appear. In so doing, much hand motion is saved. The second main technique reduces hand motion considerably from the previous techniques. In this case, instead of going over to the menu comes to us. We point to where we want the shape to appear, depress the button, and what happens is the tracking symbol, or the cross, which was previously moving, becomes anchored at the location where the button was depressed, but in its place, I have a moving menu. So what we had is the inverse of before, a stationary pointer and a moving menu. To select a triangle, I simply place the triangle over top of the marker and release the button, and it's anchored. I'll demonstrate that again. Point, depress the button. While holding the button down, and only while holding the button down, I have a moving menu, I place the item I want over the tracking symbol, release the button, and it is anchored. Again, there is a redundant version of this technique, just as there was of the previous one. In this case, we'll point, depress the button, and when I release it with a triangle, you notice the next time I depress, the triangle comes up over top of the pointer, so a simple down-up motion will get the item. The two techniques seen thus far already present a couple interesting questions. One of them has to do with the syntax of performing the selection positioning tasks. In the first technique, the dragging, we did the selection first, followed by the positioning. In the second technique, the moving menu technique, we did the positioning first and then the selection. This syntactic reversal could in fact cause problems. One may be more natural than the other. The point is, we don't really have the answer to that question, but this type of environment which we're constructing and demonstrating right now is a useful environment to actually perform the experiments to answer those questions. There's another difference or question that comes up in the two techniques, and it has to do with the number of items that can be selected. In the former technique, the dragging, where the menu is coming down the side, we generally have room for more menu items before the screen gets cluttered. As the number of menu items gets larger on the moving menu technique, the technique's effectiveness breaks down. Also, the dragging technique utilizes real estate on the display, which is not required by the moving menu technique. Therefore, in areas where display space is at a premium, perhaps the second technique is better. And finally, there's a question about the documentation. The dragging technique is fairly obvious in terms of what the user should do, but in terms of the moving menu technique, there is nothing in front of the user to prompt him as to what the course of action he should perform. The previous two techniques introduced some problems of syntax. Which came first, the selection or the positioning? The next technique which we're going to see involves the use of a character recognizer, which has the interesting property that it integrates the selection and the positioning tasks into a single gesture. We have three different symbols that are recognized by the system. For example, a check mark, as this, defines a square, an upward stroke a triangle, and a downward stroke a circle. This technique allows the user to use a simple type of shorthand and very quickly input items. The technique does have some drawbacks or important properties for the user to understand. Among them is that of the cognitive burden of remembering the different symbols. The more symbols there are, or the more items to select from, the more symbols the user must remember. This brings up the whole question of what should the symbols look like? Should they be representative? For example, in this case, why didn't I use a symbol that looked like a square, a circle, or a triangle instead of these various strokes? The answer lies in the fact that it's easier to recognize single-stroke symbols, and secondly, it's easier to draw them. If we have to draw an AND gate or a picture of a transistor or even a pictograph of such a device, the gains in using the technique are lost in the time it takes up to draw those complex symbols, even if the user can remember them. The next technique involves typing. And in the context of a graphics lab, this often is the last technique that we'll look for. What we do in this case is type a symbol to say what the shape we want, in this case an S, followed by the XY coordinates. For example, 512, 512. This will position a square in the center of the display. Now, there's a couple important points about typing. First of all, we could say it took much longer to enter that square than if I had have used the character recognizer, for example. But we have to be cautious in making that type of conclusion. If we had a subject here and we were performing an experiment to say, duplicate a picture which I've defined on a piece of paper, if the picture on the piece of paper was drawn as images, it's clear that the previous techniques would in fact be faster than the typing. But if the picture was defined as a list of coordinates, as is often the case in scientific data, then clearly typing and an experienced typist would be a much more efficient technique. Typing also has the attribute that in applications where a high degree of accuracy is required, that it often is a superior technique. Finally, the typing does not require a graphics tablet, and the cursor and so on, and therefore eliminates equipment which may be expensive or impractical in a particular environment where the application must be installed. The final point to make from this is that we have seen some cases where typing is superior to the previous techniques and vice versa. I would maintain that for every technique which we have seen, plus the next technique which we are going to see, that there is in fact a formulation of the task which would make that particular technique optimal, and there's probably also a formulation of a task which would make any technique the worst of the lot.
Early computers could be used by just one person running one program.
To overcome this inefficiency, so many people could use the machine, time sharing was developed. The obvious next step was to allow each person to run several programs.
Unix is one of the multiprogramming operating systems that now lets each person execute several programs simultaneously. But the usefulness of multiprogramming was restricted by the existing terminals. Then the first multiprogramming terminal was built.
The BLIT fully exploits the new style of operating system.
The BLIT has a 68,000 microprocessor, a quarter megabyte of memory, and a standard RS-232 terminal connection, all on one small board. 100 kilobytes of the memory is visible on an 800 by 1024 dot screen. The BLIT also has a keyboard and a digitizing mouse. I point to things on the screen with the mouse. I can also use the mouse to sweep out working areas instead of typing in coordinates. The mouse fits comfortably in the hand with its 3 buttons under the fingers. A small arrow on the screen shows where the mouse is pointing. Buttons are often used to select actions from a menu. Moving the mouse with the button depressed changes the selection. Lifting the button completes the selection, such as deleting a working area. But sometimes an extra button hit is needed to confirm the action. What are these working areas? They are called windows or layers. All share the same screen and act like regular independent terminals. I can make a new layer at any time and use it to run Unix commands. For example, I can type who to see who's using the computer. Each layer is separately programmable, so I can customize each one to a particular job, such as text editing. The editor is controlled mostly by the mouse, which selects the text, deletes it, rearranges it, makes changes. When I want to compile a program, I don't have to exit the editor. I just go to another layer and type make. It's just like another terminal on the same screen. Unix compilers are slow, so to entertain myself while I'm waiting, I can play Asteroids. You see? Compiler errors print out even while Asteroids is running.
Is graphics good for anything other than playing games?
Of course. Graphics is useful for many things, such as integrated circuit design. I can browse across the surface of a chip and instantly see design errors. Now you can see the unique advantage of this terminal. The debugger is running independently, debugging the circuit plotting program, and it stopped the program as it drew the error. Usually a debugger is a clumsy tool because it involves two separate processes, the debugger and the broken program. But a debugger fits smoothly into the BLID environment.
I've always been able to think about several things at once, but the terminal stood in the way. Through the combination of graphics and Unix, the BLID has given me access to the power of multi-programming. It is the only terminal that lets people multi-program.
This is the movie manual project. It's a prototype for an electronic book. And this is a repair manual for an automatic transmission for a car. We start at the table of contents, and I can touch parts of the transmission and get a quick description of what's in that chapter for that subassembly. I can browse around by touching other parts of the transmission and continue to get descriptions for each of these chapters. When I find a chapter that I want to see, I just touch the text, and the system will format pages for me to read. The words or phrases that are lit up in red are available as glossary words, so I can get a different definition by just touching the word, and the definition appears superimposed over the illustration. When the word that's defined has other words available for definition, I can touch them and continue to get definitions in the illustration window. Or I can touch the page corner and get back to the illustration. And I can expand the quarter frame illustration to full frame just by touching the bar in the upper left. This temporarily takes away the text and produces the same illustration as in the quarter frame, but full frame, which makes it much more readable. I can then go back to the page, and then I can leave that page. Here's another example of a page with glossary words highlighted in red. I can get a definition of these words just by touching them, and the definition will appear in the illustration corner. I can get back to the illustration, but in this case it's not a single frame, but it's actually a movie of someone coming into the frame and doing the repair that's described in the text. The two-headed slider is a speed control that allows me to watch the movie at various speeds in forward or reverse. I can stop at any point, search back to the beginning of the movie, and play at full speed. In addition, if I want to see more detail, I can expand the quarter frame illustration to full frame. The page of text is temporarily taken away, and the movie is displayed as a full frame movie. I can go back to the beginning and play the movie at full speed. And just as before, I can stop at any point, play the movie in slow motion, forward or reverse. Or I can go back to the original quarter frame illustration and the page of text. Here's another step-by-step procedure, only in this case the block of text will be highlighted, and there will be a highlight on the slider to indicate your position within the procedure, but the illustration is also a movie.
First thing to do is to loosen up the bolts carefully, not too far out. Front bolts preferably. Don't loosen them too far. If you loosen them too far, you'll have a big mess. Make sure you line the pan up under it. Best bet is do the corners closest to you. The best of the way is, if you have to loosen it up a little more, loosen the bolts by fingers, because you're going to have them all loose and, fairly loose. Not loose, but loose enough. After draining the fluid, draining what you can in the fluid by loosening the corners of the pan up, drop the pan gently, easily. Keep one hand on it, use the other hand with a wrench, and take the bolts out, one by one.
That's an example of how to do the repair the correct way. Then we have another page describing how not to do the repair. When draining the transmission oil, it's important not to loosen the pan bolts too fast or too far. If the bolts are unscrewed too far, some may come out and fall into the drip container. If the bolts are too loose, the pan may tilt open suddenly, spilling oil beyond the drip container. Or the pan might also fall off completely, making a disgusting mess.
I'm reading my morning newspaper. I'm reading it through this window, which is 1 column wide and a few lines high. You may feel this is rather an eccentric and ineffective way of reading a newspaper, and of course you'd be quite right. Because all the time I'm looking through this window I would be asking questions such as, how many articles are there in this column? Are there any interesting photographs? What other articles are there? Where's the crossword? And in general, where am I in this information space? Now, this is a silly way to read a newspaper, but it's very similar to the way in which we use a conventional visual display unit to look at one item of information in a large information space, whose periphery we could probably only just see if it was printed on the same scale as a newspaper. Now, this technique of windowing has many disadvantages. Perhaps the principal disadvantage is the absence of any context. I do not have a bird's eye view of the information to help me to decide where to focus my attention. Windowing on a particular item masks all the remaining items. There is a way of overcoming this windowing problem with its associated effect of masking. And it can be demonstrated very simply by taking our newspaper article and by adjusting the view that we have of the article. In this way, I can focus in some detail in the central region, but at the same time be aware in the peripheral regions of salient features such as headings and photographs and cartoons. In other words, I can retain a bird's eye view of the entire article. Let's apply this idea to my in-tray, an information space which is quite varied and often full of surprises. Here's a simple example in which I've used colour to indicate some property of an item. Red indicates an urgent item. The yellow one is from my secretary, and telexes are always orange. By properly designing my view of this in-tray, I can focus on one item, but at the same time be aware of the salient features of other items. The colour of each item, for example, is clearly visible in the outer regions. Thus, while perusing the contents of my in-tray, I always retain a bird's eye view of the entire contents. Now, when an item moves into the outer region, of course, it is compressed horizontally, and it is therefore very difficult to read the text. But of course, one does not want to read the text in this outer region. One wants to be aware of attributes such as colour. Indeed, each item of information has two representations. One, which is appropriate to the central region of the display and which we can read, that's a high-resolution image, and another, low-resolution image, which is appropriate to the outer regions, and where we only need to recognize perhaps a color and a letter. So if we take this representation and thread it into this structure, then we have the representations appropriate to the outer regions. If we then, in this central region, replace that image by an image appropriate to that central region, then we have the display that we're looking for. We can read that single item in the central region, but we are still aware of other items that are available in my in-tray. This manner of representing information is called the bifocal display because it has got two regions having different resolutions. The central region with high resolution and the outer regions with low resolution. And we can focus on a particular item of interest while still retaining a bird's eye view of the entire in-tray. Messages. Come in.
Hi, Bob.
Oh, hi, Mark. Have a seat. I'll be with you in a second. I'm just looking through these messages. Oh, gosh, there's one from the head of department. He wants a report on the MSc course today. I'll have to get onto that.
Did Sam leave anything for us last night?
Gosh, I don't know. Oh, yes. Gosh, it looks like there may be one here. Uh-huh.
I don't know that I like the look of that peak there very much.
No, I don't either. I think I'll leave him a message on that one. Say, check this. Yeah.
I hope I'll be able to make use of some of that in my tolerance analysis.
I think you should, yes. How's that work going on?
Well, I just need one or two more references. Yes, if I could just have one more reference on manufacturing efficiency.
Right, I know just the one you need in the transactions here. Let's see, I think it's in 78. No, it must be in 77, July. Yes, the one by director. Yes, that's it.
Oh, yes, good.
Right. I'll leave a copy of that in your pigeonhole copy.
Oh, well, thanks, Bob. I'll be able to get on with that now.
Fine, you're welcome.
Okay.
Pay attention.
Go ahead.
Load a map of the Caribbean.
As you wish. This is the disk. I'm loading your picture now. Welcome to the Caribbean. I'm waiting for you.
Pay attention.
Go ahead.
Create a red oil tanker.
Where?
There. Put a blue cruise ship.
Where?
East of the Bahamas. Make a yellow sailboat.
Where?
North of that. Create a green freighter.
Where?
East of the sailboat. Create a magenta trawler.
Where?
There. Put that.
Where?
There. Move the freighter.
Where?
There. Where is Havana?
West Central.
Where is Jamaica?
South Central.
Move the freighter.
What command?
Move.
Where?
South of Jamaica. Move the trawler.
Where?
East of the sailboat. Move that.
Where?
Where it was. Copy that.
Where?
There. Change that to yellow.
What command?
Change. Copy the cruise ship.
What command?
Copy.
Where?
South of Havana. Make that small. Make that what it was. Move that.
Where?
There. Copy that.
What command?
Copy.
Where?
South of Jamaica. Make that yellow. Make that blue.
Well, Chris, looks like we're back here in the Caribbean.
Sure does, Eric. Let's put some ships in it.
Let's give it a try. Pay attention.
Go ahead.
Create a red oil tanker.
Where?
There.
Create a blue cruise ship.
Where?
There.
Make a yellow sailboat.
What color?
Yellow.
Where?
North of Jamaica.
Create a green freighter.
Where?
North of that.
Let's try one together.
Sure, let's try it. Clear. Clear.
Proceed.
Put
that
there. Protect that.
Copy the cruise ship.
Eric, do you agree?
That's acceptable.
Thank you.
Where?
North of the Dominican Republic.
Protect that.
Protect the freighter.
Copy the freighter.
Chris, do you agree?
No way.
Thanks a heap.
You also.
The Program Visualization System, or PV, is a research prototype of an integrated graphics programming environment. PV aids the programmer in writing, debugging, and documenting software. This progress report demonstrates some of the parts of PV that have been developed to date. The present implementation uses 3 medium-resolution color displays. The right-hand screen is used for menus. The center screen is used for multiple overlapping windows, and the left screen is used for spatial navigational aids. The graphical menu of command choices has been organized using the concept of index cards. There are 3 sets of cards. The first set controls both programs and visualization binding tables. These binding tables allow PV to display animated views of running programs. The second set of cards controls the graphics editor for entire diagrams, both static and animated, objects, connectors, and other specialized components of visualizations, and a variety of text fonts. The third set of cards controls windows, grids, and a number of utilities such as the Help button. The index card format provides a strong organization for the large command set that is necessary in an integrated programming environment. Graphic symbols guide the eye to each card and help distinguish between them. The programmer selects commands from the menu by positioning a cursor over the desired command. He positions the cursor by moving a puck on a data tablet. Views of the program under development are presented on the center screen in windows which may be overlapped. A menu command allows the window to be brought to the foreground. The left screen is used for maps of the software information space called navigational aids or nav aids. Nav aids help the user maintain his orientation in the information space and allow spatial access to information, as we will see. There are 4 different nav aids. The first 3 are system requirements, system structure, and evolution or configuration control. These nav aids organize the information about a particular project. A 4th nav aid, the library, guides the user through the programming and graphics components that are shared by all PV users. Here, the user is looking at a system structure nav aid. The diagram is composed of objects representing modules and their interfaces. This is the top-level structure diagram of CCA's multi-base project. The user can zoom into any of the objects to see more detail about the corresponding module. Here, he chooses the Logical Database Processor module. This process can be repeated until reaching the most detailed level, which is the actual source code for the object. The user has exercised an option to put the result of the zoom in a new window, so he can see both the structure diagram and code at the same time. The user finds he needs to write a small sort subroutine. He makes a window for the visualization associated with this module. The PV graphics editor allows users to specify graphics interactively, but in most cases the programmer will use the PV library. The user cycles the NavAid stack, bringing the library NavAid to the top. Here is a selection of nodes in the library. The programmer has decided to use a one-dimensional array to hold the set of integers to be sorted, and he goes to the appropriate node. This node forms a special group called a cluster, a set of related components of different types. The user zooms in on the graphic template for the one-dimensional array. He makes a new window for it on the center display. Using the General Purpose Copy button, the user makes 2 copies of the array template in the graphics window. The user now fills the slots in the array templates with the name of each array, shown in white, and the name of its index, shown in gold. As each slot is filled, its outline disappears. Recall that the library clusters for arrays contain templates for graphics and code. While all templates can be accessed by zooming, as we saw before, the system also provides a command to automatically access code templates once the graphics are defined.
Hi, I'm Dave Nelson from Lawrence Livermore National Laboratory, and behind me is the Mirror Fusion Test Facility, currently under construction. As you can see, it's a rather large experiment. The building itself is about as long as a football field and maybe 7 stories tall. It's also a rather complex experiment. There's some 20-some neutral beams, about 22 superconducting magnets. Some of them are the largest in the world. and all the assorted paraphernalia necessary to control them, such as cryogenics and vacuum system and all that. And we'll be monitoring about 40,000 data points and controlling about 10,000 control points during the experimental operation. The environment is also a rather hostile one. In addition to all of the neutrons and everything, there's about 250 megawatts of power for up to 30 seconds, each 5 minutes, 16 hours a day. Since the environment is so hostile, we have to control the experiment remotely. And so we have a control room about 50 yards away to the north. So let's go take a look at it. A part of the charter of MFTF is to explore alternatives in control room design. Exactly how can we make controlling an experiment this large and complex easier and more reliable? We think we've come up with some rather innovative solutions here in that the operators control the experiment entirely through computer graphics and touch-based systems. Okay? Each operator controls his part of the experiment through one of the consoles that you see in front of you here. Each console is connected to a separate host mainframe, and this console serves as the communications link between the operator and the experimental apparatus. In fact, all communication between the operator and the computers controlling the experiment occurs through these consoles. Now, we control MFTF through a two-level hierarchy of computer control systems. A local network of 9 mainframe computers provides the supervisory control we need, and connected to this network is a network of some 80 microprocessors. It's these microprocessors that provide the real-time control and monitoring. Now, each hardware component in our system has its designated backup, so no single-point hardware failure can cause any significant downtime. In fact, we must be able to recover from any single-point failure within 5 minutes, and we found that we can do so. So let's see what one of these consoles looks like. First of all, there are the obvious physical characteristics. You have 6 screens here for viewing displays, and 2 screens down here for doing control. The screens down here are covered with a touch-sensitive surface that allows the operator to actually touch the screen and point out a button that he wants to push. Okay? In addition to that, you have some hard buttons up here for doing some of the things that you don't normally do, like stop a shot, log out, stuff like that. Okay? There's a badge reader here, and we'll talk a little bit about the badge reader in just a minute. As far as the less obvious things go, the ergonomics of this console were very carefully thought out. There's room underneath here for knees and for leg room. There's a workbench here, so you can put down your reports or your procedures, whatever you have. The touch panels are very, very easy to reach. You don't have to go out and lean over and reach things that are far away like you do in normal control rooms. The lighting up above is adjustable. Each particular console has its own individual adjustable lighting, and it's easy to maintain. Not only can you maintain the electronics in here, but you can also maintain the entire screen. Everything pulls out and can be replaced. Okay? It's important to note that all consoles are functionally equivalent. Okay? I can do the same thing here that I can do at any other console in the control room. So what actually makes the consoles different? It's the operator's access rights. Before an operator can control a console, he has to log in with his badge. Goes over, logs in, and by doing that, the software knows exactly who is at this console, okay, and configures the console especially for him. If I'm a vacuum operator, I can't control the neutral beams, and if I'm a neutral beam operator, I can't control the vacuum. If I'm the system supervisor, well, then I can control everything, and if I'm me, I can't control anything. Okay?
Hello, I'm John Fitch, MIT science reporter. We're at MIT's Lincoln Laboratory in Lexington, Massachusetts, a major research organization which has played an important role in developing this nation's defense system since World War II. And although Lincoln Laboratory is perhaps best known for its work in radar and advanced warning systems, it has also seen the beginning of the computer era and has made many important contributions to it. To learn about some of its recent work in improving the relationship between man and this important machine, we talked with Professor Stephen Coons, an associate professor of mechanical engineering at MIT and co-director of the Computer-Aided Design Project.
John, we're going to show you a man actually talking to a computer in a way far different than it's ever been possible to do before.
Surely not with his voice.
No, he's going to be talking graphically. He's going to be drawing, and the computer is going to understand his drawings. And the man will be using a language, a graphical language that we call Sketchpad, that started with Ivan Sutherland some years ago when he was busy working on his doctoral degree. And you will see a designer, effectively, solving a problem step by step. And he will not, at the outset, know precisely what his problem is, nor will he know exactly how to solve it. But little by little, he will begin to investigate ideas, and the computer and he will be in cooperation, in the fullest cooperation in this work.
Well, now, how does this differ from the way the computer has been used in the past to solve problems?
Well, the conventional way, the old way of solving problems with a computer has been to understand the problem very, very well indeed, and moreover to know at the very outset just exactly what steps are necessary to solve the problem. And so the computer has been, in a sense, nothing but a very elaborate calculating machine. But now we're making the computer be more like almost like a human assistant. And the computer will seem to have some intelligence. It doesn't really, only the intelligence that we put in it. But it will seem to have intelligence. In the old days, to solve a problem, it was necessary to to write out in detail on a typewriter or in punch card form all of the steps, all of the ritual that it takes to solve a problem.
Because the computer is so literal-minded?
Because it's very literal-minded. If you, for example, in the old days, made so much as one mistake of a comma in the wrong place or a decimal point that was omitted, the entire program would hang up and wouldn't run. But nowadays, if you make a mistake, you can correct it, as you'll see, immediately, and the computer is much more tolerant and much more flexible.
We met next with Mr. Timothy Johnson of the Design Division of the Department of Mechanical Engineering and asked him to show us this computer and its sketchpad.
We're at the TX2 console at Lincoln Lab. This machine, the large computer, was built by Lincoln Lab in 1956 as a research machine.
Now, how does this differ from a computer that would be used to run your bank account or something like that?
Well, it's designed specifically for a study of manual intervention, where the man can command the computer to take different courses of action while the program is running. You can see we have several unusual pieces of input-output equipment here. We have a scope, a knob. These are unusual at the time, and push buttons, toggle switches. We have several other related devices. This made the TX2 a prime candidate for the sketchpad developments back in 1961, and it remained a program in this machine so it would become a coherent partner in graphics so the man can communicate with the machine.
Now, how do you actually go about communicating with a computer in a graphical sense?
Well, we are using an oscilloscope here, which is much like a TV set, except it's being driven by the computer. In order to get the information into the computer, we have to draw somehow on this display, and we use the light pen. Well, in order to construct a meaningful engineering drawing, we have to have several graphical manipulations. Ivan Sutherland's programs can draw straight lines and circles.
Well, that's about what you do in the drafting equipment anyway, isn't it?
That's a very good start.
T-squared.
In order to do this, we can position this bright spot in the middle of the cross that you notice at a desired location. And we press the button to command the computer to draw a line. It will draw a line from this position, where I am now, to any subsequent position of my light pen. This is much like a rubber band stuck on two pins. One is nailed on the screen here, and the other is at my light pen. So I can position this anywhere I want. Now, I lost tracking there. I moved the pen too fast, and that told the computer to stop drawing the line. Well, if you notice, that bright dot will jump onto the line as I get close to it.
Well, the dot in the center of the cross, when you get close to the line, jumps over onto it.
Correct.
Why does it do that?
It's much like a gravity field. At the end point, it is even a higher gravity field to allow us to position the point exactly on the line, or in this case, exactly at the end point. This allows me to move my pen quite coarsely, be sloppy while I'm drawing, and get a precision drawing out at the same time. So now I'm going to draw a second line.
There you go.
And even a third one. Now, in an ordinary pencil and paper drawing, all we have is this particular picture. But the computer understands the geometry of the drawing here. What do I mean? I mean that if I point at this particular point and tell the computer to move that point by another push-button command, it will move not only that point, but all three lines that are attached to it.
And the delay between it's doing what you want it to is because it's computing all these changes.
That's correct. Now, if I made a mistake, I could delete my mistake by pointing at the line in question, for instance, and pressing the appropriate button. And it's gone. Now, I mentioned before we could draw circles also.
Right.
In order to do this, I must first indicate the center of my circle. Let's choose it to be here. And then I'll move out to an initial radius, let's say this point right here, and I press the second button to start drawing the circle. Here's our circle. Let me reduce the drawing slightly so our circle shows on the computer scope. And you see as I move the pen, it is ignoring the radial position. I've just gone off the scope screen here. The radial position of the pen and only looking at its angular position. So I can
be very sloppy as you like, in other words.
Right. In other words, the computer supplied the compass here, much like as it supplied the straight edge for the straight line.
If you go backwards, you erase it.
And I can wind it up the other way. Now, if I tell the computer to put that point right at this circle, right in that point right there, the computer knows that those must be connected. It turns out that they're not really connected. It's a very small nub there. Let me move this away and show you that they're really not connected. But I have told it by terminating the point of the pen at that position that it must be connected. Now, I can tell the computer to satisfy this constraint command by bringing in a program under command of this toggle, and watch the scope. You see now that indeed the circle is ending at that line. We have constrained the drawing to behave this way.
Well, now, I wonder if you'd expand a little more on this idea of a constraint. Just what do you mean?
All right. Let me go to a second piece of paper. Now, what I've done here is I really saved away that drawing I just drew.
Can you get it back again?
I can get it back, and I can select my drawing number by these toggles here. So I've selected a blank piece of paper, we'll call it. We have several pieces of paper. And I can, let's say I'm beginning to design. I have a very nebulous idea what I want to have in mind. Now, as I draw my part, let's say on the scope, it reinforces what I have in mind. This is, in general, part of the design process. And as I apply design criteria, stresses, and so on, eventually I will know what the exact shape of this part is. I shouldn't be required to draw the exact shape to begin with, at the beginning. I really don't know what it is. But let's say I've decided eventually in this model that I want these to be horizontal and vertical, a box. I can apply a new constraint, a horizontal constraint here, and a vertical constraint here, and a horizontal here, by pointing at the line and pressing a button. Well, now nothing has happened yet, because remember, I still must tickle that toggle over there to command the computer to satisfy these constraints.
I see. It won't actually let those rubber bands relax then until you say so.
Right. And I'll do that, and watch again. There we have a box.
Well, now, this idea of having constraints like this, being able to make lines meet or to make them horizontal or vertical, makes it quite a step ahead of something that's just a drafting machine that allows you to draw, doesn't it?
Exactly. In other words, you can get the topology down of the part, and at any subsequent position in your design, you can make it to behave exactly what you want. Straighten the drawing up. In other words, you don't have to draw exactly at the beginning like you have to do in drafting. This is, of course, just one aspect
of the program. Now what I can do, in addition to this, is call up copies of master pictures. Remember that picture we drew before? I think it looks something like that.
That's right.
What I've done is I regarded that first picture as a master. And I call up a copy of it, and I can manipulate it locally. I can reduce it, magnify it, I can rotate it, and let me place it right there. And I can do this several times. This is, of course, very instrumental for repetitive drawings like circuit diagrams or bridge bays, where we have several repetitive structures.
Oh, if you were drawing a circuit diagram, you might have little resistors or transistors or something already drawn and stored away, and you could call up as many of those as you wanted.
Right. Now, imagine that when I was doing my design work, I made a mistake in my master. Well, in order to correct that mistake, I would go back, and let's say I don't really want this circular segment to be in here. I erase it. Now I have the problem of making these changes to all the occurrences of this copy in my working drawing. This is very tedious nowadays. With pencil and paper, we have to remember where all the changes are. Now you notice, you remember the drawing, that we now have lost our circular arcs.
So if a manufacturer, for instance, of some electronic part changed the design somewhere one of these years, you could just automatically change all the drawings in which it appeared.
Correct. Well, now I've showed you many of the basic graphical manipulations we have available.
Incidentally, I would like to ask you how big this piece of paper that you keep referring to is, and how many pieces of paper you have available to you.
Well, this scope, which measures about 7 inches on the side, we regard this as a window that we can move over our paper and enlarge the size of this window. We can imagine the computer has a fixed sheet of paper behind this window. Its scale is approximately 2 miles on the side.
2 miles?
Right. And let's look at that. I can reduce this drawing slightly. And let me call up a copy of that master drawing again. Put it over the center there. Oops.
All right.
Now I've hit one stop already.
That's as small as you can. You're looking at the whole piece of paper, so.
Correct. And let me magnify it now. And now it's magnified so it's practically off the screen. Place another one in there.
Sort of like the picture within a picture within a picture idea.
Right, it's real nightmare material.
And as it gets smaller, even though the spot sort of disappears, it's really still there, isn't it?
Right, the computer has this all memorized in its memory.
Well, most of the things, though, that we live with in this world are three-dimensional rather than two-dimensional pictures like that. Is it possible to use a computer in that kind of problem?
Yes, we've expanded Ivan Sutherland's program into 3 dimensions. I have to bring that off a magnetic tape. There, we have that now. Here we have a single 3-dimensional object as seen from 4 separate views. We have a top view, as indicated by the T here, a front view, and a side view.
Oh, this is the way a mechanical drawing would be laid out, and I gather the other one is a perspective.
Right, with this addition. We can rotate this perspective separately from these 3 views to get an idea of what we have here. Now begin to rotate it. You see it's rotating about an axis perpendicular imaginary floor. We have a wireframe object here with no fabric covering. Hence we see the rearward lines as they come in behind this S, which might be lying in the surface. So but there is no fabric here, so we see everything.
When the letters go around behind, they're backwards.
Right. Now, we are drawing much like we are in 2-dimensional, except that is by moving a single point around with a light pen, but we're drawing directly in 3D. Here I have latched the pen onto the letter S. And as I move this around in the letter S, you see 4 dots moving in all the 4 views. This is the projection of the single dot.
In the side view, it's actually also following the S, but in the other 2, you're sort of looking at the S on edge, so it's just moving back and forth.
Right, and this is because the S is indeed in the plane of that side surface. So we're seeing the single dot simultaneously in all 4 views as we're moving directly in 3 dimensions.
You're just tracking in that case. Can you actually draw something in all 3 dimensions simultaneously?
Let's put a roof on this object in this fashion. We'll latch onto that corner and we'll draw a pyramid.
I can see it from the side view. It's a false front house there.
Right. And I can also distort things, move things, like we can in 2 dimensions. If I latch onto this line here, or let's say this line over here, I can pull that out to the side and distort the object slightly. Now let's see what we've drawn here. We'll rotate the perspective, this view, again.
Quite a strange looking object.
And now we have a warped house under construction, perhaps.
And there's the F backwards in the perspective. Tell me, is it possible to do, other than these simple straight line shapes, for instance, curved shapes, could you design something like an automobile this way?
We're well underway with surfaces. We've begun the programming there, and we understand them, we think, pretty well.
To learn more about the handling of three-dimensional objects in the computer, we met next with Dr. Lawrence Roberts of the staff of the MIT Lincoln Laboratory.
Well, you heard Tim Johnson explain how to construct solid objects with lines and wire figures. However, if we want to manipulate solid objects with the computer, we want to be able to represent their surfaces and so on as solid. Now here we have a representation of a piece of wood, perhaps, which is all of the lines of the sections behind each piece are hidden. As you'll see, as I start to rotate this object, the computer will place part of it behind the other part, and you will see that indeed the computer has a representation of it which knows that it's solid.
It's no longer just that wire frame. It really is solid, and when a line is behind the front surface, you just don't see it.
That's right. And so this is just one of my models that I can work with. I have a few others that I can call up. For instance, a wedge. I'll make the wedge slightly smaller and rotate it a little bit so you can see the properties of it. Now,
these fairly basic shapes.
Oh yes, you can construct quite a bit out of these basic shapes. As I move the wedge around in space, you'll see that it goes behind the solid and through it.
And the computer figures out where the lines should appear and where they should.
Where the intersection is.
You get the feeling of three-dimensional space here very dramatically, as though this were a window and there's a fore area and a behind area.
Right. Now as this comes out through the other object, you see that it indeed intersects it and can move right through it. Now we also have been working with the flow charting of programs. To instruct a computer what to do, you need to write a program.
A flow chart then would be sort of a diagram of the steps that you'd want the computer to take in solving some particular problem?
Yes, in fact, I have a flow chart on here. This is with Sketchpad again, and we have a demonstration of boxes representing statements to the computer to do some operation and compare some numbers and make a test and transfer one way or the other.
This is the way the human being would like to set it up, by drawing boxes like this that represent different computations.
This is the way that a programmer normally operates, and then he has to transcribe this to some form like cards or something as an input. But here we go directly from him drawing the flow chart and stating what each piece is, putting the statements inside the boxes, to a compiled program which he may execute on the computer.
See. Well, you've shown us how you can enter numbers, say, by a typewriter, and now we can draw things for the computer directly. Are there other ways that we'd like to be able to communicate with the computer?
Well, we've been investigating here at the lab speech recognition and handwriting recognition for enabling the person to communicate better in those ways with the computer. There are a lot of techniques which would be very useful when combined into a whole, and all of these techniques, including the graphical manipulation, will make it much easier in the future for the man to dynamically converse with a computer.
Well, thank you very much, Dr. Roberts. Today, we've been visiting the MIT Lincoln Laboratory to learn about the computer sketchpad. Our guests have been Professor Stephen Coons, Mr. Timothy Johnson, and Dr. Lawrence Roberts. I'm John Fitch, MIT science reporter.